That's why physicists do not like mathematicians, because we play with multiple dimensions, like piece of cake, and then they don't get it. They don't get it. How we do 4 dimensions over here without imagining it or being able to draw it. That's what we do. That's how cool. And we don't do just 4 dimensions. We do 5, 7, n dimensions in general. So I like the joke, triple the fun but quadruple the pain. That's not my idea, I really like it. Dr. Payam has a very good sense of humor. Calculate the following integrals where E is a tetrahedron, here's the picture below, in the first octant bounded by 6x plus 3y plus z equals 12. Sagar, you checking on my typos if I make a typo. I'm afraid I might make a typo today. I have a bad feeling. So, let's do this one. And then slowly it will introduce you to what to do with triple integrals. Step 1, draw a picture. Picture will be everything. The thing is, you ignore this part. This part is happening in 4 dimensions, so you don't draw it because it's in 4 dimensions. We don't know how to draw it. So ignore the inner part until we get to the polar coordinates. In this chapter, we don't touch this inner part at all. What we need to do is to draw this and tetrahedron. Tetrahedron is cut out by this first octant by 6x plus 3y plus z equals 12. To draw the picture, let's find intercepts of the tetrahedron with this plane. 6x plus 3y plus z equals 12 is a plane. Z-intercept means everything else is 0 except z. That's the one that survives. So it will be 6 times 0 plus 3 times 0 plus z equals 12. Remember, intercept is when everything else is 0. So z is 12. This is the place the tetrahedron touches the plane. Y-intercept, same thing. Plug 0 into 6x and 3y survives. 0 equals 12. Solve for y, which is 4. So we know this intercept. And then x-intercept will be plug 0 everywhere except x. So 6x plus 3y, now 0, plus 0 equals 12, x equals 2. We got these intercepts with the tetrahedron. Now we can start drawing the picture. This is tetrahedron in general, got cut out with the first octant, and these are the points we need to draw the picture. So, yes, sure, just a second. Like so. Oh, that's all. You need more? You need like the joke? What part are you missing?
I'm good now.
Okay. Here. No, it's fine. So the z equals, so the whole tetrahedron is supposed to go like to these places, right? But we ignore them because we only need first octant. Then, where does it touch y? At 4, we just got that. Where does it touch x? At 2, and then z at 12. That makes different, and this in blue is this plane that now have 12 minus 6x minus 3y. Z equals 0 is on the floor, and this is going to be our E. Slowly I'll try to explain you what triple integral indicates. But the idea is, before with a double integral, floor was lava. No, floor was the base of the cake. The inside part was the floating, the base of the cake. The piece inside was this floating curtain, which was, say, infinite. But we only consider it above the double integral D, area into D. What if the restricted area now is in 3D? So we're increasing a dimension. What if there's a floating curtain in 4D, and you cannot imagine it because we are dumb creatures, cannot imagine 4 dimensions really well. No, that's just the case. But that there's a floating image, say hypersphere, right? But below, there's a shadow, and the shadow is a 3D object like this one in front of you. That is the interesting thing. So there's like a volume in 4D above that 3D object. And that's what triple integral represents. Has lots of application in physics, and that's why we need to train you to do that. So step 2, now when we have a picture, we need to build inequalities to figure out limits of integration. Inequalities. The thing is, we did it before in 2D, now it will be just extra step. In general, we used to have y was between small and big. Now z will be between small and big. So let's see, z will be between a small function and a big function. I always say it's either right or left, top and bottom, but now there's a z also. Z is changing between the floor, right? Floor, and this plane. So z is between z equals 0, remember functions, and z equals 12 minus 6x minus 3y. So that's my change for z. Just a second. Do you know where I got this? That's what I wanted to ask. Do you know where I got this? Z equals 12 blah blah blah?
Yeah, from the top.
From here. Solved for z. That's what I did. Solved for z. Z was 12 minus 6x minus 3y from here. Yes?
Where did the 0 come?
0 is the first octant. Our first octant is only positive. First octant by the definition is positive z, positive x, and positive y. So the floor will be your minimum height for z. And the floor is z equals 0. Good question. So now we know limits of integration for z. We're slowly building the integral. If you want to, we do it really usually at the end, but you can slowly start building triple integral. dz will be inside, and z is from 0 to 12 minus 6x minus 3y. That's what we just did. Now we need to do y function. Y is also between a function and a function. To figure out y, we're now going to 2D. So when you're done inequalities, first you do 3D for z. We used to do it in a 2D place, and on the test you saw you draw the 2D picture, a triangle, a parabola, whatever was it. Now z requires a picture in 3D, so we're checking out this height from the floor to this plane. Now we're going to 2D. Go to 2D for x or y. In this case, we're doing y. Oh, I actually had it here. Cut. For y, we need to draw 2D picture. What is the picture of the floor of this 3D object, which is now is the base for the integral? Without considering z, let me just a second, I want to kind of have this idea finished. Look at the floor of this 3D picture. Whatever is on the floor, that is your 2D picture. That's why we call it d. So again, the integral is calculated over e. It's supposed to be like this below, over e. E is a 3D object, which plays the base of the 4D cake. That's the idea. But two of these integrals are still representing d, and d is the floor. The floor looks like a triangle. Some people are very good at it. They look at this triangle and try to flip it so it matches this notation. So you kind of like tilt your head a little bit. And I see x positive goes to 2, right? Y positive goes to 4. And then there's a connector. So kind of like some people are very good at this. If you're not, try to build the lines separately, and that helps as well. I know, right? It's shocking. So what I just said, x was from 0 to 2. We also have it from intersections over here, from 0 to 2. And y is from 0 to 4. Here's my lines. So 0 to 4. And then since it was tetrahedron, it cut it with the angle like so. And this is a triangle called D, totally like from the exam 2. So this is now we're going back to the two-dimensional situation of the base of the cake. And we need to figure out what the name of this line is. And now, questions, yes?
I was going to answer the question. I'm pretty sure this is just a y equals mx plus p line, which you can find using the difference of the 2 points in this line.
Yeah, you can find it through the difference of the points, but there's an easier way. There's an easier way, very nice way, which I personally like. Look at this function. Now, I'm just... Look at this function, 2x. You can now say that if we're taking this plane and collapsing it to the floor, so it was like a glass and you're just dropping it on the floor, that means let me check if it's, oops. That means I will, 2, divide by 3. Yeah, that's good. That means I'm shrinking this height to 0. Does it make sense? That's like the best way to explain. I like this way the best. I'm shrinking this to 0 when I'm drawing this in 2D. So I'm taking my z equals 12 minus, what was it? I forgot. 6x minus 3y in 2D is, guess what? Z is 0. So you're literally collapsing the 3D object to the floor. You're dropping the glass on the floor if it was like a wall. So it becomes 0 equals 12 minus 6x minus 3y. Simplify. 12 equals, let's not do like this. 6x plus 3y equals 12. Divide it, that's the coincidence that you can divide by something. That's what I was curious to say or not to say. But then it becomes 2x plus y equals 4. This is the line over here, which you could create using just the difference of points and stuff. The answer will be the same. 2 minus 0, 4 minus 0, you will see the same thing. So the equation of this line will be y equals 4 minus 2x. That is the line that came from the 3D plane collapsed on the floor. So when third dimension cancelled, that means z is 0. Yes?
So is z always going to be 0?
When we collapse everything in 2 dimensions, yes.
Like, yeah, in that scenario.
Yeah.
Okay.
We want to see what the shadow, like so. This is a piece of glass standing like over here towards the wall. And I want to see how much space it takes below. So I want to see the shadow of this piece of glass. How to find the shadow? You collapse 3 dimension into 0, and that gives you the shadow D. Hopefully that makes sense. So from this direction, we now can figure out dy. My y is changing between small and big. Remember, again, y is changing between small and big. So I would do it even like this. Step 1, you have the total picture. Step 2, inequalities in 3D. And then step 3, I would do like this. Inequalities in 2D. And you repeat the whole process. You build a picture and then you make inequalities. So it adds extra step at the very beginning. Now, just like on a test, I was asking you to find what the limits of integration for the y, when y is changing between a function and a function. This is how you should see it, reminding you this is not new. Y is rise, remember? It's also only Americans call it rise and run, goes up and down. So, if you want to do going from between small and big, you look up and you look down. Who is on the top? This function is on the top. This one is at the bottom, so it's a smaller one. What's the name of this function? It should be y equals. What is that? 0. So you know that. You know that. Y will be between 0 and this function we just found. How did we find? By setting z to be 0. And it's always going to be like this, at least in this chapter. So the second part of the integral, dy. So dy dx, right? Let me write down, I guess, every new thing. Integral. We did the z. Now we're doing dy, and then we're gonna finish with dx. dz was 0, 12, minus 6x, minus 3y. But y is between 0 and 4 minus 2x. Last integral should have numbers. Why? Does anyone know why, by the way?
Yeah.
Why?
Because you're always, if it's not just numbers, you're always just going to finish with another function in terms of something else.
Yeah. We're looking for the volume, like in exam 2. If you gave me the answer in terms of x and y, that was wrong. Because if we ask you volume, it should be like 3,075 cubic centimeters. It should not be x squared plus 5. How did you mess up? You switched the limits accidentally, or maybe you panicked. If the outside limits of integration are functions, the answer will be a function. And that is why you know it should be numbers. X should have numbers outside. So usually that's the simple step. To find x as numbers, let me write down number 4, step 4. And yes. Yes?
So it's always going to be like dz, dy, dx. It's not never going to be like dx.
It will be different. We will teach you how to switch, and that is why.
Like, is dy like...
I will just show you this. This is your homework.
Oh. That's nice.
It's the last problem of your homework. We need to teach you this.
Nice.
We need to teach you this. And yeah, so no, it's not always like that. It's not always like that. We need to teach you to switch between dz, dy, dx, dz, dx, dy, dx, dy, dz, dx, dz, dy, dy, dz, dx, dy, dx, dz. How many options there are? 6.
Why does lecture ruin my fun?
No, that's actually typical homework problem.
Oh, that's not good.
Yeah, that is okay homework problem.
Everyone hates web words.
So, but at least it's free. So the thing is, in 2D, we have only 2 cases. dx, dy, dx. In 3D, we have dx, dy, dz. If you ever took probability or whatever classes, we know how many choices we have. 3 factorial, that's 2 times 3, that's 6 different choices of switching the order here. dx, dy, dz, dz, dx, dy, dx, z, dx, and so on. Yes?
So I'm going to be doing that?
Yes, you will. Now, finally, last one should be numbers. Remember that. Last should be numbers, or else you will have a function as the answer, not numbers. So x is from where to where? You learn it from calculus, or you learn it from the exam 2. You just look at the x points. While y was between functions, x running between numbers. What numbers they are?
0 and 2.
0 and 2. If you don't see them, you have to find points of intersections, and you also know how to do that. 4 minus 2x intersects with y equals 0, gives you 2x equals 1, whatever, 4, so x is 2. So it's going to be from 0 to 2. To have good notes, just make a note from the triangle. From to the picture. You have, it's not new. So last 2 steps, this is old information. Only the first step was new. Finally, let's make sure we now have the integral, and we can start integrating. Now we have last step, let's call it 5, and then finally finish the integration. So we did not even start integrating yet. No integration by parts, no use substitution, trigonometric substitutions. We're only building the integral. That's how upper level this class becomes. That building a model or building a single integral takes so much understanding, 3D, graphing, having good imagination of how the plane intersects with the z-plane and the first octant and so on. What's the shadow is going to be?
dx is there. Doesn't it go at the end of the...
It will right now. So the beginning, what we gave you was looking like this. Now we decided that we are going to do this. You could switch the last 2 if you want. You technically speaking could do it this way if you want. Then dy will be at the end. Now you know how to do it. So exam 2 was about that, switching the order of integration. So the integral will be new integral. Make sure you have lots of space, because those are functions over here at the top and at the bottom. Coloring helps. The first thing I need to point out, 6z, do not touch this part. This is an object in 4D, so you do not touch that. We'll be changing it only for the polar stuff soon. Now, we decided dz goes first. That is a 3-dimensional part over here. This was coming from 3D. Z was between function, think about that, function z equals 0, and a function z equals 12 minus 6x minus 3y. Beautiful, yes. Then we decided to do dy, but you could actually do dx if you want. Just remember, numbers should be outside, no matter what choice you make. Y was between functions. Between function y equals 0 and a function 4 minus 2x. So, and the last one, let's put it in black, x was between numbers 0 and 2. Ta-da! That is the end. So this part comes from 2D. And also note, all of these are functions. Z equals, y equals, and then numbers at the end. And this is your integral. Now just the easy part starts is to actually integrate it. And we're gonna do it right now. We'll practice integration. Before practicing integration, I will just let you know what it means to have triple integrals. You don't have to write it down, just nice to have notes. In general, a triple integral does not calculate a volume. That is not why we're using it. In general, we're using it for physics and other applications. It calculates a hypervolume in 4 dimensions under the function, this function which I told you not to touch. There's a function in 4D floating. Under that function, there's a shadow, and shadow end up to be 3-dimensional now. Think about that your shadow is a 3-dimensional person. That is creepy, but that's exactly what we're doing here. If you're a 4-dimensional creature, your shadow is 3-dimensional. That's what we're doing here. So, over the 3D solid, we call it E. So, think that E is your base, and it has height 6z. Looks like that. This shadow is a 3-dimensional object. And then what is the volume below 4-dimensional object that has a 3-dimensional shadow? That is hypervolume, and that's the idea of triple integrals. Also, don't have to write this down. I'll just give you the notes. I found this nice explanation. A triple integral f dv over r. R is the 3-dimensional object. F inside is a scalar valued function that takes points in 3-dimensional space as inputs. It's the first time we have inputs be in 3 dimensions. It swallows 3-dimensional points and spits out the 4th dimension. Think about it. dv is a tiny unit of volume because we're approximating using tiny volumes figures. And then that's why we have dx, dy, dz. With double integrals, just like with double integrals, the bounds of inner integrals might be functions or of other outside variables. These bound functions are what enclose the shapes of R. And the popular application is mass. So remember when we did upper level derivatives, first derivative of the distance is a speed, then velocity, then acceleration, then jump, then this and this, and there was a jerk I think first, then jump, and at some point I think 5th derivative is like a pop, whatever. The thing is, we have it, but it's hard to imagine what is the speed of change of change of change of change of change of change of change. Yeah, it has a name pop, but what does it mean? For us as a creatures, it's hard to imagine. Now imagining undoing it with integration. The first integral gives you area. The double integral gives you volume. The triple integral gives you hypervolume, which is hard to imagine, but it does have representation in physics, and apparently it's a mass. E is the mass of the object with a density or as this function. Makes sense, and I found very nice, not example, but here, explanation. That is for my other class, don't be bothered by this. That is the exponential function growth. But I found it here. Very nice explanation of the hypervolume in general. Imagine there's a three-dimensional object. And this three-dimensional object has not the same density everywhere. What if this cube has different density? Say at the corner it has this type of density, and density is changing, maybe because it's heating up. So that's where the physics and engineering comes in. That is where the third integration comes in. Integral as the idea is not the area of volume below between graphs. Integral is the products of different values. It's a kind of smart way to multiply different things. Just like 2 times 2 times 2 times 2 is 2 to the 3, integral is 2 times 5 times negative 7 times 100. Integral collects products. So what if there's an object, even such a simple looking like this one, has different density at different corners? Double integral will give you volume of this object. Third integral will accumulate different densities at different locations. And that is kind of the cool idea. And that's where the connection between density and the mass. How heavy is this object if it's this soft in the corner but very solid at the end? This is third integral will accumulate the mass and gives you the result. That's the idea. Yeah.
How would you actually be able to see that with math bars? The only reason I'm asking is because at least the representation you have up there looks like completely even the way you cut it. So I'm not.
Oh yeah, that's different. This is what they explained here. I was about to explain. So this is they explain how. Remember when we had applications before? We were. I think it was in my announcement. Yeah. Yes, I remember now. So in my recent, of course. In my recent announcement, I actually put the animation. Did anyone see that?
No.
I'm brutally honest.
In my recent announcement, there was a saying, first of all, don't email me about your grades, and immediately someone emailed me, like immediately. Exactly 5 minutes after this announcement, someone emailed me asking for a different grade. So, this is the idea.
Professor, you should give me a different grade, 5 points less.
Leave the room. So just a second. So I was explaining this is how we approximate volumes in 3D, right? With many boxes. Let's say call them boxes. Now hypervolume will be using this common idea, same idea kind of. And that's what they're saying here. But it will be cutting through instead. So we will try to learn. It's a very good question, how do you imagine it mathematically, which I will explain slowly today and on Friday and on Monday. But the idea is we will be slicing it with, now we're using a three-dimensional object to approximate the 4-dimensional volume. That will be very interesting. Remember I showed you the animation that, imagine you have a watermelon, and every time you slice it, there is one more watermelon pops out. That's what hypervolume idea is. So same here, we will be slicing things in 4D, and we cannot even imagine the 4D. But the result will pop out with a 3-dimensional volume. But the interesting thing, even though we cannot imagine 4D object, the 4D object does intersect 3D stuff, and we are in 3D. So at least we see the intersections. And that's going to be our job, to understand how the 4D object shows up in our 3 dimensions by going through. So this idea of the ghosts being in like 4 dimensions, right? Sometimes we just see like passing by and like, oh, I saw you. Yeah, because they pass through our dimension. So if you like this idea, this is how you can imagine 4-dimensional object passing through just over here, and you saw it at the top and you saw it. And that's how you can start imagining how it looks. Kind of the idea. So let's actually calculate that amazingly looking integral. Here it is. Let's calculate it. I will move this around a little bit. Calculation is going to be your favorite part because it's nothing new. It's exactly the same we did before. 6z. So now you have to stick to the order. Why? Because they're functions as limits of integrations. Only if they're numbers you can switch the order. If they're functions, you cannot. 6z with respect to z will give you what?
3z squared.
3z squared. All agree?
Yeah.
Z squared over 2. Now, 2 integrals are waiting. That means I will have a bar, and then it's nice if you write down z equals, because now you'll have three variables, not to get confused. From 0 to 12 minus 6x minus 3y, dy, dx are waiting. 0, 0, and every time you have to rewrite everything. Equals. Plug the top minus the bottom. These guys are waiting. 3, let's kick it out. Z squared becomes 12 minus 6x minus 3y squared. D minus 0. Dy dx. Y was from 0 to 4 minus 2x. Let me change the color a little bit, at least from 0 to 2. Now it's a two-dimensional integral. You know how to do that one, do you?
Yeah. No.
The thing is, we're integrating right now with respect to y. So actually it's just one variable. It's actually chain rule. Either you actually write down as a square of this polynomial and distribute everything, or you do chain rule here. I like chain rule, so I will show you how to do chain rule. A shortcut, again, one of my amazing shortcuts is ax plus b raised to the n only works with linear ax plus b dx. A shortcut says raised to the n plus 1 divide over n plus 1 ax plus b, and then divide by the leading coefficient 1 over a plus c. That's a shortcut of the u substitution. Watch my video and subscribe. U sub shortcut. Watch, like, and subscribe. Yes. That's what Dr. Pamela says. Like and subscribe.
You put that on your syllabus.
Now, let's do this. So I'm going to divide by minus 3, as you can see. Everything else are numbers. 6x is a number. 12 is a number with respect to y. So the outside integral is keep waiting. The outside integral has 3 outside from 0 to 2 dx. This guy is waiting for its turn. The inside integral becomes copy 12 minus 6x minus 3y. Raise the exponent. It was 2, now it will be 3. Divide by 3, and then divide by the leading coefficient, which is minus 3. That's a shortcut of u substitution. But in general, you could just use u substitution. This is u, du will be minus 3, pops out, so you divide by minus 3. That was the integral. That's not done. The integral with respect to y. Bar, plugging 0 and 4 minus 2x. Since there's still 2 variables, maybe it's helpful to write down y equals 0 and y equals 4 minus 2x. The x's keep waiting for its turn. Should I slow down? What do you think?
No.
Okay, good. So it's not new. So 3 over minus third is just minus outside. I'll put minus outside. Integral from 0 to 2. Now maybe take a pencil, I don't know, whatever is better for you, and write, and then draw where you're gonna plug those numbers into y. So it's gonna be 12 minus 6x minus 3. 3 now is multiplied by a purple color, 4 minus 2x, and everything is cubed. And it's only first part. You still need to plug 0 minus. Let's put this big cube like so. Minus, open parentheses. Repeat. 12 minus 6x minus 3 times 0. I would not write this down, but just for you. 12 minus 6x cubed. And then dx is finally here. You have to check. There should be no variables y and no variables z. And the outside integral should be from number to a number. That is what I see in front of me, so I assume we did not do a mistake, hopefully. Now you distribute everything and you repeat the shortcut for the u substitution, so it's going to be 4 power over 4. Yes?
What happened to the divided by 3?
Here it is. Minus 3 cancelled out with 3, so only negative sign stays. Oh, good point. Good job, sucker. I just gave you a job today. Okay, fine. Minus, I did not see. Minus 1/3. I had a feeling I'll make a mistake. minus 1/3. But I was checking if you're paying attention. Good job for paying attention. Now let's do more. No space. Took more space than I expected. So let's simplify. You guys take a pencil, don't have to wait for me. Simplify and continue. By simplifying, I would take a pencil. It's too much rewriting every time, so it makes sense to make it faster. 12 minus 6x minus 12 plus 6x if you distribute minus 3. And now, and this one is just 12 minus 6x. Each in the cube, so you should not just merge this together. Minus 1/3 is in front, 0 to 2. Open parenthesis, 12 minus 12, very lucky, cancels out. Is all of it goes away?
Yeah, no.
Minus 6 and plus 6? Oh, that's very convenient. I did not know that. Look at that. That's just 0. Very nice. Minus, so only the second part stays. 12 minus 6x, such a good example. dx. That's a very simple integral. I would not write this down. Like, come on. Yeah. So this is 0. This end up to be 0. And I have a simple integral. Minus minus gives you plus. Do you see this minus over here? And this minus gives you plus 1/3. 12 minus 6x cubed dx. Repeating the u substitution shortcut, or you can use u substitution if you want. This will be u, but I'm doing it this way. 12 minus 6x raised to 4 over 4 and divide by the leading coefficient, which is minus 1/6 with the constant in front. 1/3, a bar from 0 to 2. The final answer should be a number. If it's a function, you messed up. So some of you gave me a function at the answer of the exam 2. That was not good. Like so. Collecting carefully all the, plug the top minus the bottom. You know this part, so I don't want to go into details. It becomes 12 to the 4 over 72, which is 288. So that's why you should be good with u substitution integration by parts, because now it comes to be an easy, fast-going stuff to do. Everything else is hard. Not u substitution anymore. Questions? I will make a pause. What do you think about this? Yes? No? Yeah, it's long. What extra step was added at the very beginning? The 3-dimensional step. Yes.
So I had a question about the density.
But what?
The density.
Yeah.
Are we finding the density of the shadow or the hyperbolic?
So the question is about density. We will be finding the mass of this solid E with the given density 2z. So 2z is in 4 dimensions. You don't imagine this object, but it has a density. And then you want to know how heavy this solid will be. E is a 3-dimensional object with the density function given. That's interesting.
So we're finding the density of the 3D object. Oh yeah, there's shadow.
No, we're finding a mass. You guys, it's an interesting question. Try to participate also. You guys, still 5 minutes. So interesting question. Look at this problem. That's going to be our second problem, so you can write it down if you want. We are looking for the mass of the solid E. E is a 3-dimensional object. This one is 3D, the one we're trying to draw. But this object has changing density. And the density was calculated in 4 dimensions. Swallows 3 dimensions, spits out the 4-dimensional result. You see? So the input is 3 dimensions, x, y, and z. The output is 4 dimensions. So how heavy is this 3-dimensional object if we know that the density over here is this way, and density over here is different, and density over here is different, and the density is described by this 4-dimensional function? That's the idea. So it's not volume below something anymore. It's a 4th quantity of the object. We have 3 quantities in 3 dimensions, right? Like front and back, up and down, left and right. That's 3 dimensions. Imagine the forced quantity, say usually it's time. How much this mass is changing with time. In this case, 4-dimensional quantity is a density of that 3-dimensional object. In this place, it's this liquid, and in this place, it's solid, and then so on. That is pretty cool. So it's no volume. Usually, we're using triple integrals not for volumes, to be honest. We're using it for the physical applications like this. Or the fourth dimension is time. How much this object is changing with respect to time. That's a triple integral as well.
So I was asking about the density of which, or the mass of which object are we finding with this triple integral? Like, are we finding the mass of the 3D object that
Yes.
is being shadowed, or the high?
No, that's exactly what I'm trying to explain. We're finding the mass of this beautiful object, right? Looks like a cantaloupe, for example. And the cantaloupe exactly has different density inside, depending on where you look at it. The density of the cantaloupe is given as so. And that's why we need triple integrals. Double integral give me the volume of this object. Triple integral will give me how heavy is cantaloupe, using this described function of the density of the cantaloupe. So no volumes anymore. Hypervolume is just nice explanation at the beginning, but in general, we're using a force quantity or the quality, or some kind of quantity, I would say, of the object. A color is changing. That's going to be fourth dimension. Time is changing. Density is changing. That's interesting. No, definitely. That's exactly what we're trying to explain. Yes.
Would it make sense to do this problem in polar coordinates?
Yes. We will be learning after this triple integrals again, right now in Cartesian, then in polar, and then in cylindrical. So not only spheres can have rotations, cylinders also have rotations. So we will be adding one more type of the integrals, cylindrical integrals, or coordinate in cylindrical integrals in cylindrical coordinates. Yes.
So, when we were doing only 2 integrals and only looking at volume, sometimes when there's like symmetry, we could just look at the symmetry. But with 3 integrals, can we not do that since it might be different?
You will see. That's a very good question. Can we see the symmetry and stuff? We will see lots of symmetry when it comes to rotations. Spheres, hyperspheres, we will do some symmetry there in polar and cylindrical. We will do some in Cartesian. I will maybe try to find an example for you. There's still symmetry, you're right. You will use symmetry in 3 dimensions only. In 4 dimensions, you don't. So, because we don't really see it. But you see intersections with a 4-dimensional object. And then you use the symmetry in 3-dimensional. So if you remember, in 2-dimensional we saw, oh, this thing is symmetrical. Let's just find the volume of this part and multiply. Now this will be in 3D, so it's not a big difference of the idea. It will be a box now. And you're like, oh yeah, let's find the half of it and multiply. But in spherical will be more interesting. It will be a sphere, and we will be doing like half of the sphere or so. So that will be more interesting. Yes.
How do you say like it's different densities inside? Like how is it different?
Density can be different. Imagine cantaloupe. Cantaloupe is somewhere like squishy, liquid, or firm at the very edges. So imagine you build a function describes how this density is changing. And it is indeed actually looking like something, animations like this. This one. When you describe some kind of behavior, this is the graph for the infected people, exponential functions and stuff. But you describe it with the function, something is changing. Density of this object is changing. You have different densities as well. The stomach, the lungs, the brain. So our own body have different densities depending on the location. So it's hard to find the mass because we're not unitary inside, just all wood, right? So if my density is changing from here to here, and then lungs and then legs are different, and then nails are solid, that means I need 4 dimensions to explain how heavy I am, and that's triple integrals. Because I am a 3-dimensional object with one more dimension changing inside of me. Or my temperature is different. Lungs have higher temperature than the stomach and so on. That's 5th dimension.
What is your integral?
Extra create problem. Calculate the integral of your body.
Is it 0? Actually,